Hello, my name is Matthew Nealon, and in this homework for homework 3, we are going to write, explain, and test code to calculate the friction factor, the head drop given flow, and the flow given the head drop for a pipe segment. So, firstly, before we begin, we're going to go through sort of an equation sheet that I made prior to the recording of this video. So, this equation sheet will give us all of the information that we need in order to calculate all of these head drops and given flows. So starting at the top, we have our Bernoulli's equation, which is going to calculate our heating from friction, which is going to be our change in the pressure divided by density. It's going to be our change in the velocity of fluid divided by 2, and gravity multiplied by the change in height. Then we have our Churchill equation, which is going to be this is something that we found earlier, which is going to be 4 times the friction factor times the length of the pipe, which is delta x, or the distance. We also have our velocity squared, and then divided by 2 divided by our diameter of the pipe. And then going down here, we have a Darcy's friction factor, which is kind of interesting because usually, at least this equation up here this was taken in terms of the fanning friction factor. But why are we using the Darcy friction factor? Well, kind of under this Churchill equation section is that this was the Churchill method to find the friction factor, at least for Darcy's equation. And so we have this equation here where our 2 theta values are actually listed as formulas. And then this is going to be our head form of the heating from friction equation, which is set equal to each other. And if you notice that our velocity of the fluid is gone, and this is because usually how this would work is that we have a pipe segment, and the diameter throughout the pipe is constant, so we're not going to need our velocity equation, and we're only using this flow, and the flow, at least what we're saying from here, is only due to the pressure differences, so we don't need that velocity term in our equation. So that's taken out, and then these two equations are set equal to each other. And coming down here, we also have our Reynolds number, we also have our flow rates, and something that we're going to be using is finding our velocity due to the flow rate, so that I've already done that calculation here. We also have something called our head drop. Head drop is sort of the distance for our flow from the pressures, from the difference in pressures. And the reason why this is negative is because of our pressure values. And the reason why that's negative is because, at least in terms of what we're going to be solving today, is that our pressure at 2 is going to be less than the pressure at 1. So we need to make sure that our head drop remains positive. So this is going to be a negative. We also have our head drop from the Churchill equation up here. And we also have, and from this, we're going to say that our head drop minus our 2 head drop equations, subtracting from each other, are going to be equal to 0. And then something that I'm going to talk about a little further is our flow rate guess for a root solver that we're going to do in our equation. So this is all the information we're going to need in order to write our code to find our flow rate and our head drop, and with our given values. So we're going to come back in. So we're going to split our screen here. We're going to split our screen, and then we're going to go over to our code laboratory. And if you can see already here, we're going to use 2 programs in this called NumPy and our SciPy Optimize, which is just going to be, NumPy is just going to be sort of just providing our natural logs, our pies, anything we need with sort of that. And then our root solver is what we're going to find our flow rate in the second part. So starting off here, the main thing we're going to need is our friction factor. So our friction factor is going to be found through this Churchill equation on the left over here. And our Churchill equation, so we're going to find a function as such. So we're going to find a function, just call it Churchill. And if you see over here that we need two things provided because of this equation. So we're going to need our Reynolds number, and we also need our surface roughness, which is just going to be E over D. But since we really can't put sort of mathematical symbols into sort of a given function, we're just going to call it E capital D. And what we're returning is going to be this thing over here. But since we're using Darcy's friction factor, since we're solving for Darcy's friction factor, we need to convert it back into the Fanning friction factor. And the Darcy friction factor and the Fanning friction factor is actually a difference from each other by a factor of 4. So we're going to have so we need to multiply this equation by 2 since this fraction of 4, and since it's already going to be included into the equation, and it's going to be it's going to be reduced down to our factor of 4. So we're going to multiply this equation by 2, and if you can tell here, we also have an exponent, so it's going to be to the 1 over 12th power, and then we're going to come back into this equation and start writing out all the terms that we need. So it's going to be 8 divided by our Reynolds number to the power of 12 plus 1 over our theta values. So we're going to say theta 1 plus theta 2. And then we're going to close that off, and then we are going to put that to the power of 1.5, which is included into the equation. And just to make sure, just sort of a preliminary, we're going to make sure that this exponent stays in the denominator. So from here, we're going to sort of work backwards with all of our functions. So our theta 1 value is going to be equal to this equation over here. So it's going to be, so that's going to be the power of 16. And in this, we are going to have 2.457 multiplied by the natural log, or numpy log, which is one of our functions we're going to be using. We're going to close this off real quick. And then this entire equation is going to be inside these natural log parentheses. So what we're going to do now is then write out the rest of this equation. So it's going to be 7 divided by our Reynolds number, and that is going to be to the power of 0.9 plus 0.27 times our surface roughness. And if you can tell, that has satisfied what we need over here. So I'm just going to look at it real quick, make sure that nothing is sort of working against each other right now. So it looks like that whole side is enclosed. All right, wonderful. All right, that should be good. Then our next value, theta 2, is going to be our equation from over here. So we're going to say that it's going to be 37530 divided by our Reynolds number. And that's going to be to the 16th. To the 16th. So this is going to be our friction factor equation. So technically, this is our friction factor with a given Reynolds number. A Reynolds number and a surface roughness. So we're just going to make sure our equation is working. So we're going to have a Reynolds number of 1600. And then just say a surface roughness of 1 to the exponent of -3. So, actually I accidentally capitalized it, which we don't want that. So if everything's working properly, we're going to get a decimal. Perfect. It's actually working as intended. And we want a small friction factor. So from here, we are going to start trying to solve the first part of it, where we're going to start solving with a given flow rate, we're going to find the head drop. So from here, we need to define a couple things. We're going to be using our Reynolds number. So we're going to be using our Churchill equation, but instead of inputting a already known Reynolds number, we're going to calculate a Reynolds number given a sort of a pipe segment. And if you notice, we have a diameter in here. So we actually need a couple things. So we need our, we need our density, we need our viscosity, and we also need our gravity. So coming down here, we set out our head drop equation as such. So we're going to define a function called head drop. And we need a couple parameters. We need our flow rates. We need our length of the pipe, which is going to be dx, but we're just going to say that's going to be the length of the pipe. We also need our diameter, and we also need our surface roughness. And then kind of working backwards, as I said before, we're going to type in our equation over here. So it's going to be 4 times the friction factor multiplied by our distance of the pipe multiplied by our velocity squared divided by 2 times our diameter times our gravity. And if I wrote everything correct here, that should be fine. Then we're going to give ourselves some space. So we're going to come back up. So from here, let's just work with our most simple variables and try to work backwards from what we have here. So we're going to find velocity first. Since we have a given flow rate, it's just simple algebra to find what our velocity is going to be. So our velocity is going to equal, our velocity equation up here is just going to be 4 times the flow rate times divided by our pi variable multiplied by our diameter to the second power. I want to come back up and get rid of some of this space here. And the next thing we need to know, oh shoot, I made a mistake real quick. I'm going to come back up here and I'm going to insert another code or another line of text in here because I mentioned it, but I completely forgot to write them out. So we need our viscosity, our density, which we're going to say is rho, and we also need our gravity. So coming back up, we're going to say that our viscosity is going to be 1 to the negative 3 Pascal seconds. And then our density is going to be 1 to the exponent of 3, or 1 times 10 to the exponent of 3. It's going to be kilograms per meter square or meters cubed, and then our gravity is going to be 9.81 meters per second squared. All right, almost forgot that. Made sure it's good that we have it now, but we're going to come back to this equation, and then we're going to find our Reynolds number. So our Reynolds number is going to be our density times our, so it's going to be our density times our velocity times our diameter of the pipe. And that's going to be divided by our viscosity, which is going to be 1, 2, which is just going to be u, since we already read it out. Just to make sure everything's properly aligned. And from here, we now need to find the flow rate. Or since we have all of our terms now, the main thing we're going to do now is then find our friction factor, which we know our friction factor is from the Churchill equation that we defined up above. So our Churchill equation is going to be our Reynolds number And then our second term is going to be our surface roughness. So this is going to be our first function to find the head drop given flow. And then we're going to come over here and make sure that our function is working. So we're just going to put in some parameters to solve this function. So it's going to be, let's say our flow rate is going to be 0.1. We're going to say our length of the pipe is going to be 10. We're going to say our diameter of the pipe is going to be 0.1. And then we're going to have a surface roughness of 5 to just the 5 times 10 to the negative 3 exponent. Come over here. Wonderful. All right, so we have our head drop. And now, since we found our first part, we now need to find our flow rate given the head drop. So we're going to do something a little similar to what we did up here, except we're going to replace this our flow rate value with our head drop value. So we're going to find a function. So our flow with our given head drop with all of our other given parameters. So we have length of the pipe, diameter, and surface roughness. Coming in here, the one thing we need to do now is that we are going to be finding we are going to be using a root solver. So if we know anything about a root solver, at least for using it in co-laboratory, is that we need a guess to find our flow rate. Or we need to put in sort of an accurate guess to find the flow rate properly. So we're going to say that we need to come up with a guess. So our flow rate guess is going to be equal to, and we're going to come down here and use what we had. And the reason why our velocity equation in this particular, in this form looks so different from the one up here is that this velocity was found with a given flow rate, but we don't have that. But we do have a given head drop, so we can find velocity that way as well. So we're going to come over here and write out our, so our flow rate guess is going to be our velocity multiplied by pi times our diameter to the power of 2. And then we're just going to make sure this is all working by putting that in parentheses, and then we're going to divide that by 4. And then we're going to put some space in here, and then say that our we've got to make sure our velocity equations are working as intended. So in here, our velocity is going to be found as such. So our velocity is going to be found by having an equation that's being to the square root. And then it's going to be our head drop. So it's going to be our given head drop multiplied by our gravity times our diameter. And then it's going to be divided by 2 times our friction factor times our delta x. So this is our velocity equation. So continuing on, gotta make sure this is working. Yeah, and that f is not what we want. So we're gonna do the same thing we did up here. So we're gonna say that our am I missing something? Sorry. I feel like I'm forgetting something. Oh, okay. I understand what I did wrong. So coming up here, we are not going to use our Churchill function again. We are just going to give, we're actually going to say that we're also going to give a friction factor as well, which is going to be 0.1, just something similar that we found up here. And the main reason why we're going to give 0.1 is because, I'm just going to write a comment, because technically our friction factor of 0.1 is also a guess in itself. But our friction factor, why we're using 0.1 is kind of just the average of our friction factors for laminar flow, because our friction factor for laminar flow goes from 0 to 0.2. So we're just going to take the middle of that. So we're just going to write out that our friction factor guess of 0.1 is the middle point of laminar flow friction factor. And there's a whole graph that shows the friction factors for both laminar flow and then for turbulent flow. But we're going to say that our pipe is in laminar flow for this time, and we're just going to say that our guess here is going to be 0.1. So we have our guess. Now we need to come back over here and try to prove that our head drop minus our other head drop equation is 0. So we need to come back over here and define a function within a function. It's kind of crazy. So we're going to find a function called equation, and then our given value is going to be x. And Q, our flow rate, is actually going to be the first value is actually going to be an array of our x value, and that first, and our x value is going to be, Q is going to be the first value of the array of x. So from here, we can then return our function and say, and we also need to make this an array as well, since we have since we're putting in arrays, and then we are then trying to find an array. So we need everything to be an array for this here. So next, we're going to say that our head drop, our given head drop, minus our head drop formula or function up here. So we're going to put that back in with a given flow. And then what do we have up here? We also have our length of the pipe, our diameter, and then our excuse me. And then we're going to have this with our surface roughness. Sorry, I wanted to finish that out. And then that should be our next equation. And then here we can actually start putting then we can have our final step of the actual root solver. So we have our equation, which is already in our vector. And then the next thing we need is our guess. So it's going to be our flow rate guess, also in an array, because we also need that in an array to get plugged into the root solver. So if that's right, then we're going to come over here and just take our head drop as our given. So we're going to say that our new function of flow is given the head drop, so 0.518, and then we're going to substitute all of our values. So it's going to be 10, 0.1, and then our surface roughness. All right, and before we enter this in, we're trying to see if our flow rate is going to be equal to what we found is going to be equal to our flow rate that we put up here in our head drop. And if they are the same, this means is that our head drop formula is coming true, and that our two head drop formulas are actually going to be equal to each other. So we are going to then, oh, actually I forgot. So we're going to say I only want the first value. And this is very good because it's not exactly 0.1, but it's going to round up to 0.1, which this shows is that our two flow rates that we found are the same, which also proves that our head drop formulas are also working as well.